Yeah, longest common subsequence. On the first hand, on the first glance, it's a completely different idea, but you will see that the problem is quite related to the edit distance, and basically we can use the same computational scheme, dynamic programming, to efficiently compute the longest common subsequence measure. So what it is about, we will see how that works. The basic idea is that we will compare two sequences by means of their common subsequence. Yeah? So two sequences may share a common subsequence or several common subsequences, and we look for the subsequence that is shared by both sequences, which has the longest length, so to say. Yeah? So the biggest length. That is longest common subsequence, as the name probably suggests, and we'll have a look now. So, idea or similarity between two sequences is defined as the length of the third sequence, which contains elements of Q and S, and is a common subsequence. Yeah, so the longer the sequence set, the higher the similarity between Q and S, and vice versa, of course. Yeah? So attention, this is now a similarity measure, because the longer the sequence is, the higher the similarity. So the higher the measure, the longest subsequence measure is, the higher the similarity. So that is a similarity measure rather than a distance measure, where it's the other way around. Yeah? A distance measure means, for a distance measure, it means that a small value is high similarity. Yeah? So here's an example. We have these two sequences, Q and S, whatever that is, and you see that a possible solution for the longest common subsequence is this the subsequence which is highlighted in red in both sequences. Here it is again. So it's G T C G T blah 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 blah. So okay, you can just try to compute or prove that, okay, I hope you believe me, that is actually the longest common subsequence, the longest sequence set, which contains elements from Q and S. Yeah? And there is no longer such a third sequence set containing elements of Q and S. Yeah? So that is the idea. We're looking for that common subsequence, third sequence, which contains elements of Q and Z, and we look for that which have the highest length, yeah, which is the longest of those third sequence. So the formalization is a little bit more, well, not tricky, but a little bit more exhaustive. So we need a sequence as a subsequence of another sequence if there is a strictly increasing sequence of indices, which are denoted here by I1 to IK, such that, yeah, for all indices j from 1 to k, it holds that we have an element from Q and an element from Z with the same indices, so to say. Yeah. So maybe we just look at an example here. So here is the Q sequence, and this sequence set here is actually a subsequence of Q, because there is such an increasing sequence of indices, which is actually, well, B. The index of B here in Q is 2. The index of C is in Q is 3. The index of D in Q is 5, and the index of this B here in Q is then 7. Yeah? So we can find an index sequence in Q such that the elements of Z are at these index positions in Q. Yeah, yeah. Just this footnote here, that we start, of course, our indices by 1 and not by 0. Yeah, but anyway, I hope that explains the idea of a subsequence. Yeah. And a sequence is a common subsequence of two sequences if it is a sequence of both of these sequences. Okay, well, that's I guess easy. So we need a corresponding index sequence for both of these two sequences. It need not to be the same. Yeah, so the common subsequence may have different indices for Q and different indices for S, of course. Yeah, but there need to be such an increasing, strictly increasing index sequence. Yeah. Okay, now given that, okay, we can define the problem of the so-called problem of longest common subsequence. That is to find a maximum length common subsequence of two given sequences Q and S. Yeah, so for example here we have Q and S, and if we have a look at this sequence here, BCA, okay, that is a common subsequence. This one here is a common subsequence of Q and S. But if we take a closer look at that, it is not the longest one, because we have, for example, BCBA, so BCBA here and BCBA here. So this is a subsequence also for those two sequences Q and S, which is longer than this one here. So this length here is 4, and this length is 3. So this is longer than this one here. Obviously, there's another one which has a length of 4, BDAB, BDAB. Okay, sounds good. So yeah, so there are longer ones. So we're looking for the longest subsequences. Yeah, so that is the longest subsequence problem. And then of course the longest common subsequence measure is the length of those longest common subsequences. And again, as the same as in the edit distance, there can be more than one longest common subsequence of two sequences, obviously. Now, the LCSS measure, longest common subsequence measure, is defined as, we see it here. So it's 0 if either n is 0, so Q is empty, or S is empty. So this is again a recursive formula, and we see, okay, if we have one of those two, that is the base cases. Those are the base cases for the recursion. If one of those two sequences is empty, then obviously we have no common subsequence. Yeah, so the longest common subsequence have length 0, so it is a 0 common subsequence, obviously. Yeah, so if Q is empty and S has M objects, then the longest common subsequence is 0, because, yeah, obviously, and the other way around. Yeah. If not, then we are in the recursive cases. Then again, we look at this at the last element, like in the edit distance, and say, okay, if the last element is the same, then we have found at least one element for the longest common subsequence. So we add 1 and compute the longest common subsequence for the prefix of Q and the prefix of S, obviously. Yeah? And well, if the two last elements are different, then we have to, well, keep the last one of S and compare it to the remaining Q's. Yeah, so that is the second part. Or we take the last element of Q and compare that with the second next from S, and that is the first one here. Yeah, so we have these two recursive steps, and of course we look for the maximum in those two cases. But anyway, if the two last elements from Q and S are not equivalent, we cannot add 1 here, because we haven't found a match so far. Yeah, so in that case now we're looking for matchings, and I think this formula somehow explains it, or it's quite intuitive in that case. Yeah, so we look for the last elements. If they are equal, add 1. If not, we have to move on with one of the two sequences. So those are the two alternatives that we have, and we take the maximum in that case, of course. Yeah, looks pretty similar like the edit distance, and actually it is very similar, or the computation is quite similar. So the computational time complexity can be reduced to, again, O of n times m through dynamic programming. The same idea as before, that we use this matrix notation and work from top left to bottom right with a very similar closed formula that we had before. Yeah, and we can do that basically in the same way as the added distance. Yeah, the downside of LCSS is that it is not a distance measure, and very often methods just use distance measures and not similarity measures. And also a second downside is that LCSS highly depends on the length of the analyzed sequences, of course. Yeah, so if you have long sequences, the probability that the longest common subsequence has a long length is, so to say, also high, is of course much higher than if the corresponding sequences, or at least one sequence, is small, yeah, has a low length. So there's a kind of dependency on the length of the analyzed sequences. But we cannot do too much about the last part. Well, we can normalize the whole thing and make a distance function out of it, and that is that is shown here. So we take the LCSS of two sequences and normalize it between 0 and 1 by just dividing it by the number of by the minimum of the two lengths of Q and S. Yeah. And then still we have a similarity measure. So in order to reverse it, we take 1 minus this one here, yeah, because we know this fraction here, of course, is between 0 and 1. Yeah, so this is the normalization to the interval between 0 and 1, and then we take 1 minus this one here, which gives us a distance function, a distance measure. Yeah, so if the two sequences are perfectly equal, then we have a 1 here, and we have 1 minus 1 is 0. Then we have a distance of 0 in that case. Yeah, so that makes sense, probably. Okay, and the distance also is between 0 and 1, obviously. Yeah, and then I just want to show you a generalization of the longest common subsequence, which is also again very popular in bioinformatics, where we have multiple alignments between several sequences. So not only two sequences here in the argument, so to say, in the input parameters, but we may have multiple ones, for example, K. Yeah, so we look for the longest common subsequence of K sequences. And then the complexity is a little bit harder, so it's 2 to the power of k times n to the power of k for k sequences, and n is the length of the longest common, the longest sequence. The longest sequence. Yeah, so it's shown here with this bioinformatics focus here. So that is very often done by bioinformaticians. Just that you know. Yeah, you can also, of course, play here with multiple sequences at once, so to say. Yeah, last word on mining sequence data. So distance-based data mining views the entire sequences as single observations. Yeah, you can use one of the distance measures from above, or variants of them, or other ones to compare sequences. You can do clustering, outlier detection, classification of sequence data with these distance measures. However, in that case, you do not really mine sequential patterns. You only mine patterns of similar sequences. I mean, you account for the sequence nature of these sequences, but you don't really mine sequential patterns. So if you want to mine sequential patterns, you, what are sequential patterns? That are usually frequently occurring subpatterns within a set of sequences. And in that case, you typically apply counting the frequency of these subpatterns in sequences. Subpatterns are subsequences again. So you count the frequencies of subsequences in sequence objects and report those. Yeah, so that is a kind of generalization of frequent item set mining. The only difference to frequent item set mining, where the occurrence, the order of the occurrence of the items in the market basket, in the transactions, is of no interest. Here now the order of the occurrence of the elements of course matters, because you look for specific subsequences in some specific order. Yeah? However, the algorithms are very, very similar to the frequent item set mining problem. Yeah? So that is the big picture. If you apply distance-based data mining, you can do that with these distance measures. If you want to apply, or if you want to find sequential patterns, you typically use algorithms from frequent item set mining for that purpose. Yeah? Okay,